You input a prompt and the system executes smoothly until it suddenly seizes and outputs a glaring error mid-process. Modern large language models produce text that reads as deeply intelligent, but they lack conscious comprehension, belief systems, or any internal mechanisms to verify if what they are saying is true. This creates a frustrating reality for operators. One prompt yields a brilliant, flawless analysis, while a nearly identical prompt produces a highly confident hallucination. Many prompt engineers approach this problem by treating the AI as a conscious reasoning engine or a flawless database retrieval system. AI behavior is not a mysterious black box. It is an emergent property of interacting statistical traits. To achieve reliable, enterprise-grade integration, operators have to stop relying on blind prompt guessing and learn the exact mechanical limits of the system. This engine is built from 4 specific mechanical layers that dictate every output. These 4 foundational blocks are prediction, knowledge, memory, and steerability. System contradictions and hallucinations arise from predictable interactions between these specific layers. We are going to construct this engine layer by layer to map exactly how these structural traits interact. Visualizing the AI as an engine of overlapping parameters allows you to shift from a reactive state of frustration to a proactive state of systems engineering. The bedrock action of all modern generative AI models is a process called next token prediction. Instead of planning a complete paragraph, the AI calculates the statistical probability of the next word fragment, branching out into hundreds of possible subsequent pathways. The absolute directive of the system is to always select the highest probability pathway forward, ignoring all other branches. Unlike human reasoning, this mechanism optimizes strictly for linguistic plausibility, not factual accuracy. Because it focuses only on the immediate next step, it lacks a long-term architectural plan for the output. The text generates blindly into the future without a global map. This perfect mimicry of reasoning patterns creates highly fluent text, but the system possesses 0 built-in mechanisms to verify if the predicted text is actually true. Because the system optimizes for plausibility over truth, you must build your own external truth verification loops directly into your workflows. The second layer is the knowledge base. AI knowledge is encoded in probabilistic weights, not structured as a Boolean database lookup. These massive, glowing peaks indicate heavily reinforced clusters of widely represented data, known as strong knowledge. In contrast, these deep, dark valleys represent weak knowledge, areas mapping niche or rare topics where the training data is sparse and the resulting pathways are fragile. Failure occurs when a user prompt forces the system out of a strong peak and down into a weak knowledge valley. Even in these valleys, the system must still predict the next token to maintain linguistic plausibility. To bridge the gap in a weak knowledge area, the system invents nodes. This is fabricated knowledge, a hallucination that maintains the flow of the sentence. These hallucinations are dangerous for operators because the system delivers them with the exact same linguistic confidence as its strong knowledge. Treating a language model like an omniscient database guarantees brittle outputs. You must evaluate the knowledge density of your specific domain before trusting the system. The third layer of the engine is working memory, which operates strictly through the system's context window. This context window acts as a bounding box, representing the absolute limit of information the AI can hold at any one time. As the AI generates more text, the window slides forward. The earliest nodes fall outside the rear of the box and instantly decay. When this slide occurs, critical early prompt instructions, persona constraints, and negative parameters are physically pushed out of the system's memory. You experience this when an AI starts strong but eventually contradicts itself, drops formatting rules, or abandons the initial goal midway through a long output. To avoid memory overflow, operators must continuously restate vital constraints or break complex workflows into smaller, independent chunks. Without active context management, operational alignment will inevitably degrade over time, no matter how precise the initial prompt was. The final layer is steerability. This is the system's mechanical sensitivity to the phrasing, tone, and structural constraints of your prompt. A user instruction acts as a localized gravity well, forcefully bending the natural probability tree towards specific linguistic outcomes. These 4 traits, prediction, knowledge, memory, and steering, do not operate in a vacuum. They interact and collide. High steerability often overrides knowledge. A prompt can powerfully pull the pathway away from a secure peak and drag it directly into a valley of fabricated knowledge. If you impose heavy formatting constraints on a topic the AI barely knows, the system is forced to confidently hallucinate to satisfy the prompt's rules. Similarly, when working memory constraints collide with steerability, complex formatting instructions are abandoned late in an output because the rules have slid out of the context window. Bizarre or incorrect behavior is the predictable result of these underlying system properties colliding. Once you understand the architecture of the engine, you can actively repair it using a programmatic diagnostic flow. The diagnostic flow begins by checking knowledge and prediction for missing data or mathematical flaws. Next, verify if memory dropped instructions or lacked steering gravity. Finally, check for property collisions forcing a hallucination. By sequentially walking through this matrix, you elevate your workflow from random prompt tweaking to precise, targeted systems engineering. This systematic understanding of the AI engine informs the 4D framework, a methodology for managing all AI interactions. Delegation involves assigning tasks based on the system's knowledge peaks, while description applies the necessary steerability to warp the probability map toward the desired outcome. Discernment uses the diagnostic matrix to evaluate predictive errors, and diligence maintains operational alignment by managing the context window over time. Operating these systems effectively requires treating them as probabilistic linguistic matrices rather than intelligent entities. Ultimately, reliable AI performance comes from deeply understanding, anticipating, and engineering around the predictable limitations of the machine.